I want you to just take a second and look down at your hands right now.
Just really look at them.
Yeah, because before there were cells in the skin you're looking at, there was literally no biological memory on this planet. I mean, before there was chemistry, there were no atoms to even bind together.
Right. And if you keep pulling that causal thread backward, before there were planets to stand on, there was nowhere for a liquid medium to exist, to spark life.
Exactly. And before there were stars to forge all those heavy elements, there was no night sky at all. It was just a dark, expanding fog of raw, unstructured hydrogen.
Which is pretty mind-bending to think about.
It really is. So the mission of our deep dive today is to basically trace that specific thread. We are tracing the 13.8 billion year narrative of how a hyper-compressed, unimaginably hot early universe cooled, stretched, organized, and burned itself into galaxies, oceans, and, well, minds capable of asking questions.
It's the ultimate origin story.
It fundamentally changes how you look at yourself, I think, when you realize you aren't just this entity existing inside a static universe. You are literally the universe currently studying itself.
You are. It is this unbroken chain of cause and effect. But we should probably establish a crucial baseline immediately. This origin story isn't about everything just popping into existence all at once, fully formed like some cosmic parlor trick.
Right, no magic wand.
Exactly. It is a story of thermodynamics. Honestly, the unsung hero of the entire 13.8 billion years is the slow, relentless process of cooling.
Cooling, I love that.
Yeah, it's just this constant chain of gathering, collapsing, burning, shattering, and beginning again.
So let's start at that very beginning, 13.8 billion years ago. We have this concept that fundamentally breaks our primate intuition, which is the Big Bang.
Oh, the nomenclature is notoriously terrible.
It really is, because it implants this image in your head of a localized explosion.
Yeah.
Like a firecracker detonating inside a massive, dark, empty warehouse.
Right. And that image completely fails because it assumes an empty stage waiting to be filled. There was no warehouse. There was no pre-existing space for the universe to expand into. So the foundational concept you really have to grasp here is metric expansion.
Okay, metric expansion.
Yeah.
Right.
The Big Bang was not an explosion of matter moving through space. It was the expansion of space itself.
Which means there is no central point of origin, right? Like, you can't point to a spot in the night sky and say, oh, there it is.
No, absolutely not.
So if you were standing on Earth or on a planet in the Andromeda Galaxy or, in a galaxy 10 billion light years away, you will observe the exact same phenomenon.
Yep. On the largest scales, everything else appears to be receding from you.
Because the distance between the galaxies is increasing. The grid itself is stretching.
Exactly. The grid is stretching.
The analogy I find most helpful here because, well, it avoids the pitfalls of the classic expanding balloon or the baking raisin bread analogies, which still kind of imply an edge, is the infinite rubber ruler.
Oh, I like the ruler analogy.
Yeah, so imagine a ruler made of infinitely stretchable rubber with little ants standing on the inch marks. The ants are entirely stationary. They aren't walking.
Right, they're just sitting there.
But if you grab the ruler and stretch the rubber itself, the distance between the 1-inch mark and the 2-inch mark increases. The ants haven't walked anywhere, but they are suddenly further apart.
That captures the metric expansion perfectly. The galaxies, by and large, are like those stationary ants. They are bound locally by their own gravity, but the fabric of space-time between them is continuously generating more distance.
And because of that expansion, we arrive at the thermodynamic engine of creation you mentioned earlier, which is cooling.
Yes. The unsung hero.
So let's unpack the mechanics of that cooling, because it's not just a passive drop in temperature on a thermometer. It is the absolute prerequisite for any kind of structure.
It is. When we talk about heat in the early universe, we are talking about extreme kinetic energy.
Just violent movement.
Exactly. Everything is vibrating and colliding with such ferocious intensity that no fundamental forces can actually bind anything together. Thermal agitation completely overpowered the strong nuclear force. It overpowered electromagnetism.
So if the universe had just stayed at that initial temperature, it would have been permanently frozen in a state of hyper-energetic chaos.
Just a perfect, featureless plasma forever. But by stretching space, the universe diffused that energy over a larger volume. The ambient temperature dropped, which meant the kinetic energy of all those particles dropped.
And once things slow down, the fundamental forces finally get to have a say. They can start pulling things together.
Right. Gravity and electromagnetism can finally do their jobs.
I do want to touch on the boundary of this model, though, because the inevitable question always arises, what caused that initial expansion? Or, what was there before the Big Bang?
The boundary where our current physics simply breaks down entirely.
Right. It's frustrating.
It is, because general relativity beautifully describes the macroscopic stretching of spacetime, and quantum mechanics describes all the subatomic particle interactions. But as we rewind the clock closer and closer to absolute zero time, the universe becomes both unimaginably massive and infinitely small simultaneously.
And the math just sort of gives up.
Essentially, yes. The math of both theories produces infinities. They stop making logical sense when you combine them under those conditions.
Plus, asking what happened before time began might just be a structurally flawed question, right?
Exactly. If spacetime is a unified fabric, and that fabric began expanding 13.8 billion years ago, time itself is a property of the universe.
So to ask what came before the universe is like standing on the North Pole and asking someone to point north. The geometry of the question just collapses.
That's a great way to put it. Science operates on evidence, and the observable evidence paints a very clear empirical picture. The universe was once infinitely denser, it was infinitely hotter, and it has been expanding ever since.
So let's step into fraction of a second after that expansion begins, because we immediately hit one of the most vital and arguably bizarre phases of cosmology. Cosmic inflation.
Oh, inflation is wild.
It really is. This is the period where space stretched so rapidly it defies normal comprehension. We are talking about a microscopic region of space expanding to macroscopic proportions in, like, a trillionth of a trillionth of a trillionth of a second.
Which I know sounds like it violates the core tenet of physics.
Right, the speed of light limit?
But going back to your rubber ruler analogy, it actually doesn't.
Right, because the ants on the ruler have a strict speed limit. They can only walk so fast. Nothing can travel through space faster than light.
But there is no theoretical speed limit on how fast the rubber ruler itself can stretch. Space can generate new distance between 2 points at a rate that far exceeds the speed of light.
It's just a loophole in physics, basically.
Yeah. Sort of, yeah. And that inflationary period solves several massive observational problems for us. It explains why the universe looks so uniformly distributed on a large scale, and why space-time appears geometrically flat rather than curved.
Because it just ironed everything out.
Exactly. Inflation took a chaotic, curved, microscopic patch of space-time and stretched it out so violently that any extreme curvatures were essentially ironed flat. It left behind this incredibly smooth distribution of energy.
Smooth, but crucially not perfect. And those microscopic imperfections are, well, they're the only reason we are having this conversation today.
Yes. Quantum mechanics dictates that nothing can be perfectly still or perfectly uniform. At the subatomic level, there is always this baseline level of jitter, quantum fluctuations.
This constant vibrating.
Right. And during that incredibly violent period of inflation, those microscopic subatomic density variations were suddenly frozen and stretched to cosmic scales.
It is like taking a tiny digital photograph and zooming in a billion times. The smooth image suddenly reveals all its jagged, pixelated imperfections.
That's it, exactly. Those imperfections meant that some regions of the early universe were infinitesimally denser than others, a fraction of a degree hotter, a fraction of a percent more massive.
And gravity finds those spots.
It does. Over the next several billion years, gravity would act on those tiny density variations. Denser regions exerted a slightly stronger gravitational pull, drawing in more matter, which in turn increased their gravity, creating this runaway feedback loop.
It's amazing. A microscopic quantum whisper amplify into the architecture of the entire cosmos. Those fluctuations became the seeds of the galactic superclusters we see today.
They really did.
But before we get to galaxies, we have to deal with a universe that is basically a blindingly hot fog.
Right. We are now a few minutes after the initial expansion. The universe has cooled just enough for quarks to finally bind together.
The strong nuclear force finally wins out over the heat.
Exactly. It overcomes the thermal agitation, snapping quarks into triplets to form the very first protons and neutrons.
And here we hit the era of Big Bang nucleosynthesis. Protons and neutrons are just smashing into each other, attempting to build heavier atomic nuclei.
But the conditions are incredibly finicky at this point. Free neutrons decay rapidly in about 15 minutes. To survive, they have to bind with protons.
So they formed deuterium and then rapidly fused into helium-4.
Yes. However, the universe was expanding and cooling so quickly that the density and temperature dropped below the threshold required for sustained nuclear fusion within roughly 20 minutes.
Wait, 20 minutes. That's a wildly short window for the universe to play with chemistry.
It really is. And because of that incredibly short window, nature hit a bottleneck. There are no stable atoms with a mass of 5 or 8. To jump the gap and build heavier elements like carbon or oxygen, you need a sustained high-pressure furnace.
Which the early universe didn't have the time for. The expansion just shut the furnace off.
Exactly. So the output of Big Bang nucleosynthesis was incredibly basic. It was roughly 75% hydrogen nuclei, 25% helium nuclei, and just a microscopic trace of lithium.
That was the entire periodic table for millions of years.
That was it.
No carbon for cellular structures. No oxygen for water. No iron for planetary cores or, blood cells. Just the absolute rawest building blocks.
And importantly, these were just bare nuclei. We didn't even have complete atoms yet. The ambient temperature was still thousands of degrees.
So the universe was filled with this dense plasma of these nuclei free-roaming electrons and photons of light.
Which made the universe entirely opaque.
A cosmic pinball machine.
Totally. A photon of light could only travel a fraction of a millimeter before slamming into a wildly energetic, negatively charged electron, and it would just scatter off in a new direction.
So if you could somehow survive standing in this era, you wouldn't see anything. The mean free path of light was basically zero. It's just a glowing wall.
This opaque, glowing plasma state persisted for roughly 380,000 years. The universe continued to expand, the rubber ruler kept stretching, and the ambient temperature steadily fell.
Until it hit a critical thermodynamic threshold, right? Around 3,000 Kelvin.
Yes. The era of recombination. The thermal kinetic energy of the electrons finally dropped below the electromagnetic binding energy exerted by the positively charged protons.
So the electrons were moving too slowly to escape. They basically got captured by the nuclei, locking into orbit.
Exactly. The first stable, electrically neutral atoms of hydrogen and helium were born.
And because the electrons were suddenly bound to specific energy levels within atoms, rather than just roaming freely acting as a shield, the photons were no longer obstructed.
The fog instantly cleared.
I love that visual. For the first time in cosmic history, light could travel in a straight line.
And that specific flash of light, released at the exact moment the universe became transparent, has been traveling through space for 13.8 billion years. We can actually still see it.
It is the cosmic microwave background. And the mechanics of how we see it today perfectly illustrates that metric expansion we talked about.
Right.
When those photons first decoupled from the plasma 380,000 years ago, they were intensely energetic, visible light. Mostly this brilliant, searing orange.
But they have been traveling through space that has been stretching for billions of years.
So as the space stretched, the wavelength of those photons stretched along with it. A short, energetic wave of visible light was elongated into a much longer, lower-energy microwave.
Which is why we call it the cosmic microwave background today.
It fundamentally changes how you look at a static TV screen. When you realize you're looking at the literal boundaries of time.
Yeah.
I mean, you grew up with analog tube televisions and remember tuning to a dead channel? A small fraction of that black and white static was your antenna interacting with those exact photons.
You were literally watching the cooled, redshifted afterglow of the Big Bang itself.
Wow.
And when cosmologists map that microwave background today using highly sensitive satellites, they don't see a perfectly uniform temperature. They see those microscopic temperature fluctuations we discussed earlier.
The quantum jitter.
Right. Frozen in time, showing us the exact blueprint of where the dark matter was beginning to clump together.
Which transitions us into an era that sounds deeply ominous but is mechanically just fascinating. The Cosmic Dark Ages.
Very dramatic name.
It is. The fog is cleared, the universe is transparent, light is traveling freely. But there are no stars yet to produce new light. It is just a vast, expanding ocean of neutral hydrogen gas plunging into darkness.
But a universe made purely of evenly distributed gas is a dead universe. To build planets, you need heavy elements, and to get heavy elements, you need a furnace.
Which brings us to the most crucial role gravity ever played, driven by this invisible scaffolding. Dark matter, the structural framing of the cosmos.
It really is the framing. We know from the gravitational dynamics of galaxies today that the ordinary baryonic matter, the protons, neutrons, and electrons that make up gas, dust, stars, and us, it only accounts for about 5% of the total mass energy of the universe.
Only 5%. That's humbling.
It is. Dark matter makes up about 27%.
And it is non-baryonic. It doesn't interact with electromagnetism at all. It doesn't emit, absorb, or reflect light. It doesn't even interact with ordinary matter through friction, right?
No, is essentially a ghost, except for one crucial property. It has mass, therefore it exerts gravity.
Without dark matter, the universe as we know it could never have formed. If the early universe only contained ordinary hydrogen and helium gas, the thermal pressure of that gas, that natural tendency of warm gas to expand outward, would have easily overpowered its own weak gravity.
The gas would have never collapsed to form stars.
It needed a gravitational anchor.
Precisely. Dark matter provided that anchor. Because dark matter doesn't interact with radiation, it wasn't pushed around by the intense light of the early universe. It could begin clumping together much, much earlier.
So it formed these massive invisible gravitational wells, which are known as dark matter halos. The house framing analogy works beautifully here. When you walk into a finished house, you are looking at the drywall, the paint, the electrical outlets. That is the ordinary matter. You don't see the wooden studs behind the wall.
Right.
But without those invisible studs bearing the load, the drywall would simply collapse under its own weight into a pile on the floor. Dark matter was the invisible studs.
I really love that analogy. The gravitational pull of those dark matter halos acted like massive funnels. They began dragging in the ordinary neutral hydrogen and helium gas. And as the gas fell into these halos, it compressed.
And as it compressed, the gas molecules collided more frequently and the temperature began to soar.
Because the mechanics of star formation are essentially a high-stakes battle between gravity trying to crush a cloud of gas into a singularity and thermal pressure pushing outward.
So for millions of years in the Dark Ages, gravity kept pulling, the gas kept compressing, the core temperature kept rising, until the core of one of these gas clouds hit roughly 10 million degrees Celsius.
The ignition point.
At 10 million degrees, the kinetic energy of the hydrogen protons is finally high enough to overcome their mutual electrostatic repulsion.
Right, because protons, being positively charged, naturally want to violently repel each other. But at this temperature and pressure, they slam together so hard they actually fuse.
The strong nuclear force takes over again. Hydrogen fuses into helium. A tiny amount of mass is converted into a staggering amount of pure energy, following Einstein's E equals mc squared.
And that energy radiates outward, providing the outward pressure needed to halt the gravitational collapse. The star achieves hydrostatic equilibrium. The cosmic dark ages officially ended when the first population thirst stars ignited.
I really want to focus deeply on these population 3 stars because they were nothing like our sun. Our sun is a third-generation star. It is relatively small, stable, and laced with heavier elements like carbon, oxygen, and iron.
Right, but population 3 stars had zero metallicity.
Zero.
In astrophysics, anything heavier than helium is referred to as a metal. These first stars were purely hydrogen and helium. And that lack of heavy elements dictated their bizarre mechanics.
Because heavy elements in a gas cloud act as a coolant, right? They are incredibly efficient at radiating thermal energy away into space in the form of infrared light.
Exactly. Because the primordial gas clouds had no heavy elements, they couldn't cool down efficiently as they collapsed. A hotter gas cloud has higher outward pressure.
So to overcome that massive thermal pressure and force a collapse, the cloud had to be exceptionally massive.
Which means these first stars were absolute monsters, hundreds, perhaps up to 1,000 times the mass of our sun.
That is terrifying.
And in stellar physics, mass dictates lifespan. A star that massive has a core under such excruciating gravitational pressure that it burns through its hydrogen fuel at an astronomical rate.
So while our small sun will burn steadily for 10 billion years, a massive population third star might burn out in just a few million years.
It's a flash in the pan, cosmically speaking. But in that short lifespan, they acted as the fundamental engines of creation. They were the true alchemists of the universe.
They solved the bottleneck of Big Bang nucleosynthesis. Inside the core of these massive stars, once the hydrogen is depleted, the core contracts, the temperature spikes even higher, and it begins fusing helium into carbon via the triple alpha process.
The universe finally learns complex chemistry.
Yes.
Then carbon fuses into oxygen, neon, magnesium, silicon. The core of the star develops these concentric, onion-like layers of fusion, building heavier and heavier elements, pushing outward against the crushing weight of its own gravity.
Layer by layer until it hits iron.
Ah, iron. Iron is the absolute cliff edge of stellar nucleosynthesis.
To get to the line.
Exactly. Fusing elements lighter than iron releases energy, which supports the star. But iron is the most tightly bound nucleus in nature. Fusing iron doesn't release energy, it absorbs it.
It is an endothermic reaction. So the moment a massive star starts producing an iron core, it literally signs its own death warrant. The outward pressure of nuclear fusion is instantly cut off.
With the fusion engine suddenly deactivated, gravity wins unconditionally. The entire outer envelope of this supermassive star collapses inward at a significant fraction of the speed of light.
Trillions of tons of plasma crash into the dense iron core simultaneously.
But the core physically cannot compress any further. It halts the collapse.
So the infalling material hits that incompressible core and bounces outward, generating a shockwave of unimaginable power. A supernova.
And the mechanics of that shockwave are vital to us. As the shockwave rips outward through the outer layers of the star, the temperatures and pressures become so extreme, far beyond anything achievable in a stable stellar core, that a process called rapid neutron capture, or the R process, takes place.
Right. Free neutrons slam into existing nuclei so rapidly they don't have time to decay. In those brief seconds of a supernova explosion, elements far heavier than iron are forged. Gold, platinum, uranium.
And the explosion shatters the star completely, scattering all of those newly forged elements, the carbon, the oxygen, the silicon, the iron, the gold, deep into the interstellar medium.
It enriched the pristine hydrogen and helium gas. It seeded the cosmos with the chemical building blocks necessary for rocky planets and ultimately organic biology.
The ashes of those fierce, short-lived giants became the raw material for everything we consider normal today.
And they did one other vital thing, didn't they? The intense ultraviolet radiation from these stars stripped the electrons away from the neutral hydrogen gas surrounding them.
Yes. Reionization. The gas became a transparent plasma once again, finally ending the Dark Ages and clearing the space for light to travel unhindered through an increasingly structured universe.
Because gravity didn't stop with individual stars, dark matter halos merged into larger superhalos. Gas flowed along the invisible filaments of the cosmic web, pooling into massive gravitational intersections. These concentrations of stars, gas, and dark matter became galaxies.
It is a classic model of hierarchical merging. Small structures gravitationally attract each other and collide to form much larger structures.
Now, I want to address a major point of public confusion regarding this era, because anyone following astronomy news recently has seen the headlines about the James Webb Space Telescope.
Oh, yes, the clickbait headlines.
Yeah. Webb has been peering deep into the infrared, looking at galaxies that existed just a few 100 million years after the Big Bang. And the headline scream, "Webb finds early galaxies that are too big. The Big Bang is broken." Does the discovery of mature galaxies so early in the timeline mean this 13.8 billion year model is wrong?
No. That is a fundamental misunderstanding of how the scientific method processes new data. The Big Bang theory is absolutely not broken. The metric expansion of space, the cosmic microwave background, nucleosynthesis, all these pillars remain mathematically and observationally solid.
So what is Webb actually breaking?
What Webb is breaking is our assumption about efficiency.
Efficiency.
Precisely. Our previous computer simulations, based on older Hubble data, assumed a certain rate at which dark matter halos gathered gas, and a certain rate at which that gas could cool and collapse into stars. We expected early galaxies to be small, messy, and chaotic.
So finding these massive, brightly lit, structured galaxies so early is like finding out a human child learned to write complex literature at age 2 instead of age 6.
Great analogy. It doesn't mean the child wasn't born. It doesn't mean human development is a lie. It just means the specific mechanism of neurological development in that era was wildly more efficient than our models predicted.
Webb is forcing astrophysicists to refine the mechanics of early star formation.
Exactly. Perhaps early supermassive black holes acted as massive catalysts for star formation rather than shutting it down. Perhaps the initial gas was far denser than modeled. Science is not about confirming a dogma. It's about building better instruments to find where our models fail so we can build better models.
Which brings us to our specific corner of one of those models. Out of the chaos of merging dwarf galaxies and collapsing gas clouds, the Milky Way formed. It is just one of roughly 2 trillion galaxies in the observable universe. But inside one of its spiral arms, about 4.6 billion years ago, a very specific sequence of events unfolded.
Yes. We are looking at a giant molecular cloud. It is cold, dense, and crucially enriched with the heavy metals from generations of long-dead supernovae.
Right, and the formation of a solar system relies heavily on the conservation of angular momentum. As gravity caused a localized region of this cloud to collapse inward, any slight rotation it had was dramatically amplified. much like an ice skater pulling their arms in.
The bulk of the mass plummeted into the center, compressing and heating up to form a protostar, which became our early sun. But the rotational forces prevented all the material from falling straight in. The remaining gas and dust flattened out into a spinning accretion disk around the young sun.
This protoplanetary disk is where the mechanics of planet formation play out, and thermodynamics again takes the lead. We have to look at the frost line.
Right, also known as the snow line. Near the young sun, the temperature in the accretion disk was incredibly high. The intense stellar radiation and the friction of the colliding particles meant that volatile compounds, things like water, ammonia, methane, they could only exist as gas. They couldn't condense into solids.
Only materials with incredibly high melting points, silicate rocks and heavy metals like iron and nickel, could condense into solid grains in the inner solar system.
And those solid grains of rock and metal began to collide. Through electrostatic forces, they stuck together, forming pebbles. Pebbles collided to form boulders. Boulders gravitationally attracted each other to form planetesimals, and planetesimals smashed into each other in a chaotic molten demolition derby to form rocky protoplanets.
Because metals and silicates are relatively rare in the cosmic inventory, these inner rocky planets could only grow so large: Mercury, Venus, Earth, and Mars.
But if you travel further out in the accretion disk, past the orbit of Mars, the thermodynamic environment drops below a critical threshold, the frost line.
Out here, it was cold enough for water, ammonia, and methane to undergo deposition, right? Transitioning directly from a gas to a solid ice.
Yes. And because these hydrogen-based compounds were massively more abundant than rock and metal, the planetary cores that formed out here had significantly more building material. They grew rapidly, reaching roughly 10 times the mass of the Earth.
Once a solid planetary core reaches that specific mass threshold, its gravitational pull becomes strong enough to achieve something the inner planets couldn't. It begins rapidly sweeping up the raw hydrogen and helium gas directly from the solar nebula.
Runaway accretion. They swell into the gas giants and ice giants, Jupiter, Saturn, Uranus, and Neptune.
So the architecture of our solar system is a direct result of the temperature gradient in that early disk.
Exactly. It's all about cooling.
So returning to the inner disk, Earth formed roughly 4.54 billion years ago. But the early Hadean eon Earth was not a hospitable blue marble.
Not at all.
It was a terrifying, hyper-volcanic hellscape, completely molten from the kinetic energy of constant asteroid bombardments and the decay of radioactive elements in its core.
And it was about to suffer the most catastrophic impact in its history. The mechanics of how we got our moon are deeply tied to the stabilization of our planet.
The giant impact hypothesis is currently our most robust mechanical model, right?
It is. It posits that a Mars-sized protoplanet, often named Theia, formed in a similar orbit to Earth. Eventually, their gravitational interactions destabilized, and Theia collided with the young Earth at an oblique angle.
The kinetic energy of that impact is staggering. It melted both planets entirely. The core of Theia sank and merged with Earth's core, while a massive fraction of Earth's outer silicate crust was vaporized and blasted into orbit.
That superheated ring of debris eventually cooled and accreted through gravity to form the moon.
And we know this mechanically because lunar rocks retrieved by the Apollo missions show an isotopic signature for oxygen that is virtually identical to Earth's mantle.
Right, heavily implying they were formed from the exact same mixed reservoir of material.
But the moon isn't just a dead rock in the sky. It fundamentally shaped Earth's future. The impact knocked Earth off its vertical axis, giving us the 23.5-degree axial tilt that creates our seasons.
And the gravitational pull of the newly formed, incredibly close moon acted as a gyroscopic stabilizer. It prevented Earth's tilt from wobbling wildly over millions of years.
It provided a stable climatic environment. As the heavy bombardment phase of the early solar system slowed down, the Earth's surface finally began to radiate its heat into space. The magma ocean cooled and solidified into a basaltic crust.
And then the ultimate catalyst for biology arrived: water.
Volcanic outgassing released massive amounts of water vapor that had been trapped inside the Earth's mantle during its formation.
Additionally, icy comets and carbonaceous asteroids continuously delivered water from beyond the frost line.
As the atmosphere cooled, this vapor condensed. Torrential rains fell for millions of years, cooling into the first global oceans. The importance of water cannot be overstated here. From a mechanical perspective, a dry, rocky planet is geologically and chemically static.
Right, it's just a rock. But water is an astoundingly unique molecule. It is a dipole.
Meaning what, exactly?
The oxygen atom pulls the shared electrons slightly closer to itself, giving the oxygen end of the molecule a slight negative charge and the two hydrogen atoms a slight positive charge.
Because of that polarity, water is the universal solvent. It can pry apart the electrostatic bonds of salts and minerals, dissolving them into solution. It provides a fluid, dynamic, three-dimensional medium where complex molecules can drift, collide, and interact without being locked rigidly in place or burned apart by extreme heat.
And somewhere within that chemical soup, non-living organic chemistry transitioned into self-replicating biology, abiogenesis.
The exact spark remains unknown, but the mechanics of the leading theories are fascinating. We aren't really looking for a magic lightning strike in a shallow pool anymore, are we?
No, the most robust model points to alkaline hydrothermal vents at the bottom of the primordial ocean.
These vents weren't the superheated black smokers we often picture. They were cooler, porous chimneys made of carbonate rock. They continuously pumped warm, highly alkaline fluid into the acidic, iron-rich early oceans.
That interaction creates a natural chemical gradient, a difference in pH between the inside of the porous rock and the ocean outside.
And that proton gradient is the fundamental battery of all life. Even today, every single cell in your body relies on a proton gradient across a membrane to generate ATP, the energy currency of biology.
Right, these deep-sea vents provided a natural geological battery. They concentrated organic molecules in tiny rocky pores, providing the energy and the structure for basic RNA and lipid membranes to organize themselves.
It is the moment matter organizes itself into a system that can fight back against entropy. Life emerged roughly 3.5 billion years ago. We see the fossilized evidence in stromatolites, which are these layered mounds formed by shallow water microbial mats.
And for over 1 billion years, Earth was a biosphere entirely dominated by anaerobic microbes. They lived in an atmosphere devoid of free oxygen, relying on elements like sulfur or iron for their slow, inefficient metabolisms.
Until a specific branch of microbes, cyanobacteria, developed a biochemical engine that would forever alter the trajectory of the planet. Photosynthesis.
Yes. They evolved a complex protein chain capable of capturing the kinetic energy of a photon of sunlight and using that energy to rip a water molecule apart.
They strip the electrons from the hydrogen to power their cellular machinery. But the byproduct of stripping water is free oxygen, O2.
And this introduces a massive biological paradox. Oxygen, to an organism that hasn't evolved to handle it, is a highly reactive, corrosive, deadly radical. It steals electrons from organic bonds, literally tearing cellular machinery apart.
It was the Great Oxidation Event, the first biological pollution crisis on a planetary scale.
Initially, the Earth acted as a chemical sponge. The oceans were full of dissolved, unoxidized iron. As the cyanobacteria pumped out oxygen, the oxygen reacted with the iron, forming iron oxide, rust.
Massive quantities of rust precipitated out of the water and sank to the seafloor, creating the banded iron formations that supply modern steel industries today.
But eventually, those geological sinks filled up. Between 2.4 and 2.0 billion years ago, free oxygen began bubbling out of the oceans and accumulating in the atmosphere.
It triggered a mass extinction of the anaerobic microbes. It also reacted with atmospheric methane, which is a potent greenhouse gas, destroying it and plunging the Earth into a massive glaciation known as a snowball Earth event.
But biology is endlessly adaptable. While oxygen is a deadly poison, it is also incredibly eager to accept electrons. Certain surviving microbes evolved enzymes to neutralize oxygen's toxicity, and eventually they figured out how to use it.
Aerobic respiration. The mechanics of this shift are why we have complex life today. Without oxygen, breaking down a molecule of glucose yields a net of exactly 2 molecules of ATP energy.
But if you use oxygen as the final electron acceptor in the metabolic chain, you can fully oxidize that glucose molecule. The yield jumps from 2 ATP to roughly 36 ATP.
Wow. It was the shift from burning wet wood to burning high-octane rocket fuel.
That massive increase in available energy allowed cells to grow larger. It allowed the formation of eukaryotic cells, where a host cell absorbed an aerobic bacterium that eventually became the mitochondria. It allowed cells to stick together, communicate, and differentiate their functions. It allowed for multicellularity.
Without the catastrophic pollution of the Great Oxidation Event, biology would never have had the energy budget to build an animal, which perfectly sets the stage for biology to invent visible, macroscopic drama, the Cambrian explosion.
Around 541 million years ago, the fossil record shifts dramatically. For 3 billion years, life was microscopic or simple, soft-bodied organisms. Suddenly, over a span of just a few tens of millions of years, the ancestors of nearly all modern animal phyla appeared in the oceans.
This wasn't just an increase in numbers, though. It was the invention of the ecological arms race.
Mechanically, the oceans reached a critical threshold of dissolved oxygen and calcium. Animals evolved biomineralization, the ability to extract calcium carbonate from the seawater to build hard structures.
Armor. Shells, spines, exoskeletons. And if you are building armor, it means something's trying to eat you.
Right.
Prior to the Cambrian, ecosystems were mostly passive grazers living on microbial mats. Now you have active predation.
And predation drives exponential evolutionary pressure. The Cambrians saw the development of bilateral symmetry, directed motion, and arguably the most important sensory input in history, the eye.
The evolution of light-sensitive proteins into a directional photoreceptor fundamentally changed survival. If a predator can see you from 10 feet away, you can no longer just sit there.
No, you have to evolve to swim faster, burrow deeper, or grow thicker armor. The mechanics of predation force life to complexify its nervous systems.
The neural networks required to process visual data and coordinate muscular evasion laid the groundwork for complex brains. Life became an active, high-stakes competition.
And eventually, that competition pushed life out of the oceans. The development of the ozone layer, created by ultraviolet light striking all that atmospheric oxygen, finally shielded the land masses from lethal solar radiation.
Plants colonized the continents, their roots mechanically breaking down rock to form the first soils. Arthropods followed, then lobe-finned fish hauled themselves out of the water, evolving into amphibians and early reptiles.
But the path of complex life is deeply contingent on external, chaotic interventions. Evolution is not a ladder climbing toward a predetermined goal. It is a constant adaptation to the immediate environment. And occasionally that environment changes so violently that the dominant adaptations become fatal liabilities.
Mass extinctions, the grand reset buttons of biology.
The most catastrophic was the Permian-Triassic extinction, roughly 252 million years ago. Massive volcanic eruptions in what is now Siberia released oceans of magma and ignited vast coal beds, pumping staggering amounts of greenhouse gases into the atmosphere.
The oceans heated up, circulation stopped, and the water became deeply anoxic. Roughly 90% of all species on Earth were annihilated.
But the void left behind provided an ecological blank canvas. In the reorganized, arid ecosystems of the Triassic period that followed, a specific clade of archosaurs evolved an upright posture, tucking their legs directly beneath their bodies rather than sprawling to the side.
It made them incredibly energy efficient on land. The dinosaurs arrived.
They dominated the terrestrial biosphere for over 150 million years. They adapted to shifting continents and changing climates, evolving into the massive sauropods and the feathered theropods.
And their reign highlights the fragility of the evolutionary path. The dinosaurs didn't die out because they were evolutionary failures. They were superbly adapted to their environment.
They died out because of orbital mechanics.
66 million years ago, a carbonaceous chondrite asteroid, roughly 10 kilometers across, slammed into the shallow waters of the Yucatan Peninsula at 20 kilometers a second.
The Chicxulub impact. The kinetic transfer of that impact vaporized the asteroid and thousands of cubic kilometers of Earth's crust, which happened to be rich in sulfur.
It created a global shockwave, ignited continent-spanning wildfires, and lofted a massive cloud of soot and sulfur dioxide into the stratosphere, blocking out the sun for years.
The resulting impact winter collapsed the base of the food chain. Without sunlight, photosynthesis stopped. The plants died. The massive herbivores starved. The apex predators starved. Every non-avian dinosaur was wiped out.
Consider the implications of that event for us. The asteroid didn't create mammals. Small, shrew-like mammals had been living in the literal shadows of the dinosaurs for over 100 million years.
But they were relegated to the margins, nocturnal, insect-eating, hiding in burrows or trees.
The asteroid simply removed the dominant competition. It cleared the board. With the dinosaurs gone, the surviving mammalian lineages suddenly had access to an empty world.
They underwent a massive adaptive radiation. Over millions of years, they evolved to fill the vacant niches. Some mammals grew massive and took to the open plains. Some adapted a streamlined shape and returned to the ocean, evolving into whales.
Some took to the air as bats, and some stayed in the complex, three-dimensional environment of the forest canopy, the primates.
Right. Navigating a forest canopy requires very specific biomechanical adaptations.
You need binocular vision, forward-facing eyes, to generate the overlapping fields of view necessary for precise depth perception so you don't miss a branch and fall to your death.
You need grasping hands with opposable thumbs rather than claws to manipulate branches and forage for varied food sources. And crucially, processing that 3D visual data and coordinating those complex motor skills requires a highly developed, expanded cerebral cortex.
The environment demanded neurological complexity. And as shifting climates over millions of years caused the dense African forest to thin out into sprawling savannas, some of those primates were forced to adapt to the ground.
Bipedalism emerged. Walking upright on two legs is a highly energy-efficient way to traverse long distances across an open savanna.
But more importantly, bipedalism permanently freed the hands.
Once the hands are no longer required for locomotion, they can be utilized entirely for manipulation. Hominins began picking up rocks, striking rocks together to create sharp edges.
The first technology. And this triggered a massive evolutionary feedback loop. Tool use allowed early hominins to access high-density calories, like bone marrow left behind by apex predators.
A higher calorie diet supported the metabolic demands of an even larger brain. A larger brain created more complex tools and complex social structures, which demanded more calories, driving the cycle further.
Over millions of years, various hominin species migrated, adapted, and eventually went extinct, until roughly 300,000 years ago, anatomically modern Homo sapiens emerged in Africa.
Thus,
And for roughly 95% of our existence as a species, we were nomadic hunter-gatherers. We harnessed fire, we pounded on cave walls, we observed the cyclical movements of the stars. We were deeply integrated into the local ecology. But driven by extreme climate fluctuations at the end of the last ice age, human populations in fertile river valleys began a new experiment. Instead of following the food, they used their cognitive architecture to engineer the environment to produce food, agriculture.
the ability to generate a caloric surplus meant that for the first time in human history, not every single member of the tribe had to dedicate their entire day to finding food.
A caloric surplus allows for specialization. Some individuals could dedicate their time to building permanent structures, creating the first cities.
Some could dedicate their time to tracking the seasons, leading to mathematics. Some could invent abstract symbols to record grain surpluses, leading to written language.
From the invention of writing to the splitting of the atom, it took just a few thousand years, a microscopic fraction of a cosmic blink.
We transitioned from biological evolution to cultural evolution. Information was no longer stored solely in DNA. It could be stored in clay tablets, books, and eventually servers, passed down and accumulated across generations.
Which brings us to the profound philosophical milestone of this entire 13.8 billion year narrative. For nearly all of cosmic history, the universe blindly churned. It expanded, it collapsed, it burned, it froze. Chemistry reacted mechanically. Biology mutated randomly.
But through a long, fragile chain of thermodynamic cooling, stellar nucleosynthesis, chemical gradients, and evolutionary pressures, a localized pocket of matter organized itself into a neurological system complex enough to achieve self-reflection.
Hydrogen became thought. The atoms surged in the cores of dying offend. Population third stars had assembled into eyes to look through lenses and brains to calculate the expansion rate of space and vocal cords to ask, how did I get here?
The universe began to study itself. It is the ultimate reduction of entropy locally, an island of complexity processing the history of the whole.
But the more we look outward, the more we realize how deeply strange our reality is. Which brings us to the mysterious present. Here we are 13.8 billion years in. The sun is a middle-aged yellow dwarf calmly fusing hydrogen. Earth is teeming with life. But when cosmologists tally up the total mass energy density of the universe today, we are confronted with a deeply humbling statistic.
Everything we have just discussed, the quarks, the atoms, the stars, the planets, the water, the biology, is made of baryonic matter. And baryonic matter accounts for only 5% of the universe.
We are a rounding error. The rest of the universe is dominated by forces we cannot see and do not fully understand. We already discussed dark matter, which makes up roughly 27% and acts as the gravitational glue holding galaxies together.
But the remaining 68% is something far more bizarre: dark energy.
For a long time, astrophysicists assumed that the gravitational pull of all the matter in the universe would eventually slow down the metric expansion that started with the Big Bang. But in the late 1990s, observations of distant supernovae revealed exactly the opposite.
The expansion is not slowing down. About 9 billion years after the Big Bang, the expansion of the universe began to accelerate.
Whatever is driving that acceleration, we call it dark energy. It behaves like an intrinsic property of space itself. As space expands, more dark energy is created, pushing space apart even faster. It is a cosmological constant pushing outward against gravity.
And if dark energy continues to dominate, it dictates the ultimate fate of the universe. If the metric expansion continues to accelerate indefinitely, the universe is heading toward a state of maximum entropy, the Big Freeze.
The mechanics of the Big Freeze are frankly terrifying. As space expands faster and faster, distant galaxies will eventually recede from us faster than the speed of light, disappearing beyond the observable horizon. The night sky outside our local galactic group will go completely black.
Locally, the stars will eventually exhaust their nuclear fuel. The giant stars will go supernova. The smaller stars, like our sun, will shed their outer layers and leave behind slowly cooling white dwarfs. Eventually, the gas clouds required to forge new stars will be depleted.
Star formation will cease entirely. The white dwarfs will cool into black dwarfs. The universe will be populated only by dead stars, rogue planets, and black holes.
And over unimaginable timescales, even the black holes will evaporate through Hawking radiation. The fundamental particles themselves may decay. The universe will become a vast, near-infinite void containing nothing but a thin soup of photons and leptons, slowly approaching absolute zero. No energy gradients will exist. Nothing will ever happen again.
It induces a profound sense of existential dread, doesn't it?
It is a sobering thermodynamic reality. But we must ground this in the perspective of time. The timescales involved in the Big Freeze completely erase human meaning. We are talking about trillions of years in the future.
So we are incredibly early in the story.
We live in the stelliferous era, the era of starlight. The universe is currently incredibly bright, dynamic, and chemically rich. Galaxies are interacting, stars are actively forming, planets are settling into stable orbits.
And regarding the mysteries, the fact that 95% of our universe is composed of dark matter and dark energy that we fundamentally do not understand, I have come to view that not as a failure of science, but as an invitation.
Exactly. It proves that the universe is still vastly larger than our current conceptual frameworks. The fact that the foundational equations of cosmology still have massive unsolved variables means the adventure of discovery is nowhere near its end.
So let's synthesize this staggering journey. Let's bring the 13.8 billion years back down to the scale of the human being listening right now. We started by asking you to look down at your hands.
The phrase, "we are made of stardust," is frequently utilized as poetic imagery, but astrophysics demands we interpret it as literal physical reality. The atoms organizing your biological functions right now were not generated inside your body. They are ancient, inherited artifacts.
The hydrogen in the water molecules lubricating your joints was forged in the first 3 minutes of the Big Bang. It has remained unchanged for 13.8 billion years.
The calcium hardening the bones in your hands was synthesized in the nuclear furnace of a massive star that detonated billions of years before the Earth even existed.
The iron capturing oxygen in your red blood cells was created in the crushing final milliseconds of a supernova core collapse.
You are physically constructed from the exact cosmic history you are attempting to comprehend. To look up at the night sky through a telescope is not to look outward into a void that is separate from you. It is literally looking backward in time, observing the very sequence of physical events that made your current biological moment possible.
From the rapid metric stretching of space to the thermodynamic drop that allowed quarks to bind, from the invisible dark matter framing that pulled gas into the first stellar engines to the supernova shockwaves that seeded the cosmos with heavy chemistry.
From an accretion disk of dust forming a molten Earth to the exact chemical gradients of deep-sea vents that sparked self-replicating life.
Through the toxic crisis of oxygen, the evolutionary arms race of the Cambrian, the catastrophic asteroid that cleared the board for mammals, down to the primates who freed their hands to build tools, write equations, and launch telescopes.
It leaves a final, grounding thought to process. Tonight, if the sky is clear, walk outside. Stand in the dark, look up at the stars, and remember that you are not merely a passive observer standing on a rock. You are 13.8 billion years of thermodynamic history that has finally organized itself well enough to ask the universe, where did I come from?
In a very real mechanical way, human curiosity is the cosmos attempting to understand itself.
Which begs the ultimate question, what will it understand next?